Hello. In this video, we're going to look at how we can do some basic operations using radical expressions. So let's consider first what happens when we want to multiply together two mixed radical expressions. What we need to consider first, so for example, 2 root 5 times 9 root 10, is that multiplication is associative and commutative. So I can move this around a little to consider that, because this is all just multiplication, 2 times root 5 times 9 times root 10. So I can consider this to be 2 times 9 times root 5 times root 10. So the 2 times 9 part, that's easy, that's 18. Root 5 times root 10, remembering that square roots are basically just exponents, and since I can distribute an exponent over a multiplication, I can also distribute a radical over a multiplication. I can treat this as root 5 times 10. That's obviously 50, but I'm not going to bother doing that multiplication because when I want to simplify a radical, I want that radical to be factored. So when I factor 10, it has 5 and 2 as factors, which means I have a pair of factors right here. So that simplifies to 18 still out here, 5 times the square root of 2. But now again, I have multiplication being associative, so wherever in these brackets is kind of arbitrary, I can do 18 times 5, which is 90, times the square root of 2, which is now the simplified version of that multiplication. It's similar for cube roots. I'm going to first look at this as 12 times 5, and then the cubed root of 21 times 63. Again, I'm not going to do that multiplication because I'm going to consider the factors here. This is 3 times 7. 63 is 7 times 9, which is 3 times 3, perfect square. So in terms of cubic, because remember we're dealing with cubes here, so I want groups of 3 similar factors. So I do have 3 threes, which means that I can simplify this. Now the 12 times 5 is 60, and I'm now going to have a 3 out here. And then inside, cubed root of 7 times 7, which is 49. So I have 180 times the cubed root of 49. When I have variables, it's essentially the same. So here, I'm actually going to use the exponent laws. So this is going to be the cubed root of x to the power of 8, because 5 plus 3 is 8, square root, not cubed root, and y to the power of 8 plus 5 is 13. When I simplify this, I'm looking for pairs of factors. So I can think of y as being y to the power of 12 times y, because 12 is an even number, and then I have sort of a remainder of 1y. The square root of x to the power of 8 is x to the power of 4, because remember the square root is like an exponent of half. So half of 8 is 4, half of 12 is 6, so I have y to the power of 6, but I do have an extra y left over inside that square root. So that is the simplified form here. For division, I can do it basically the same way as multiplication. I'm going to consider this first. I'm going to simplify this fraction, 175 over 35. Because I can see that 175 and 35 both divide by 5, I'm going to do that first. So 175 divided by 5 is going to be 35. And 35 divided by 5 is 7, but I can see that I can simplify this even further. So this is just square root of 5, which is already simplified. I don't have to do anything beyond that. So I didn't recognize right off the bat that 175 divided by 35 was 5, but I got there by stages. If I have mixed fractions or mixed radicals in my fraction, I can treat the whole number portion and the radical portion somewhat separately. So 3 over 6 is 1/2. Obviously, 12 over 3 is 4, so this is times root 4. But I know that root 4 is 2, so this is 1/2 times 2, which is just 1. So this whole complicated fraction here is just equivalent to 1. Let's say I have 6 over 8, root 8 over root 6. So again, same idea, 6/8 is how I'm thinking about this, and then 8/6. I'm going to simplify each of those fractions individually. So this becomes 3/4, and then the square root of 4/3. Square root of 4 just is 2, so I have root 2, 3 times 2 in the numerator, 4 root 3 in the denominator. So 6 over 4 root 3, but now I can actually simplify a little further because 6/4 simplifies. So I have 3 over 2 root 3. Now this technically is simplified. However, as a standard, we don't like to have radicals in our denominators. There's a somewhat historical reason for this, that division by a rational denominator is easier to estimate than division by an irrational denominator. Obviously, it doesn't really matter in an age of calculators, but because we do have multiple different representations of fractions that are possible, the one that we accept as sort of the standard representation is one in which we have rational denominators, so no square roots in the denominator. In order to do that, remember that I can modify fractions by multiplying numerator denominator by the same value. So what I'm going to do here is I'm going to multiply it by the square root of 3. What this accomplishes is, well, my numerator is just going to be 3 root 3. But in the denominator, root 3 times root 3 is root 9, which is just 3. So these two together are just 3. So 2 times 3 gives me 6. And then I actually have one final step I can do here, because 3 over 6 is the same thing as 1 over 2. So this is the final fraction, which is equivalent to 6 root 8 over 8 root 6. That's a little trickier when I have a cubed root in my denominator, because if I just do what I did there and multiply by the cubed root of 25 over the cubed root of 25, which is just multiplying by 1, which doesn't change the value, what I've then created in the denominator is the cubed root of 625, which is not a cube, it's not a perfect cube. So this doesn't actually help me. What I can do instead, there's two different ways I can go about this. I can multiply by the cube root of 25 squared, because then what I'm going to create is the cube root of 25 cubed, which is just 25. And that will work, and then I'll have to simplify down. But what I'm actually going to recognize here is that 25 is already 5 squared. So in other words, I already have a square number there, so I really only need to multiply it. So I'm going to erase all of this here. I really only need to multiply it by one more 5. So what I'm going to do is I'm going to multiply by the cubed root of 5. Because when I do that, I'm dealing with smaller numbers for one thing. That won't always be possible, but here it is. When I do that, my denominator is now going to be the cubed root of 25 times 5, which is 125, which is a perfect cube. So the cubed root of 5 in the numerator can't simplify, but the denominator now just becomes 5. So now I have a fraction in which my denominator is a rational number. With multiplications and divisions, we can use the fact that we can rearrange, and we have the distributive property of essentially a radical over a multiplication or division. But as soon as we put additions and subtractions in there, it works differently. I'm going to ask you to consider, what if I had 3x minus 5y plus 9x plus 2y? So essentially, I've just rewritten this using x for root 7 and y for root 5. Now, most of you are probably aware that this is going to then be just adding together like terms. So 12x minus 3y. And it is exactly the same in this radical instance. So I get 12 root 7 minus 3 root 5. The reason that works is essentially commutativity, as well as the reverse of the distributive property, factoring out a common factor. So just to kind of show the steps here, this is, I'll do it with the radicals. So if I treated this as 3 root 7 plus 9 root 7, so just changing the order, minus 5 root 5 plus 2 root 5. These two factors have these two terms have a common factor of root 7 times 3 plus 9. That is where the 12, because 3 plus 9 is 12, times root 7 comes from. And these two have a common factor of root 5 times negative 5 plus 2. And that is where the minus 3 root 5 comes from. So we can only add and subtract together radicals that have, oops, that is the question, not the answer. We can only add and subtract together radicals that have the exact same radicand. That's the root 7 or the root 5. In instances like this root 175 minus root 63, it kind of then looks like there's nothing I can do about it, because these are not similar terms. However, if I simplify first, then I will be able to do that. So I'm going to write these as factors. They're perfect squares, so I'm looking for perfect square factors. So 175 is 25 times 7, and 93 is 9 times 7. So that means that I can express root 175 as 5 root 7 because it's the square root of 25 times the square root of 7. And I can express root 63 as 3 root 7 because it's the square root of 9 times the square root of 7. Now they are similar terms, so I can subtract the coefficients. 5 minus 3 is 2 root 7. If I wanted to re-express that as a whole radical, it doesn't say here I have to, so there's no real reason, but just in case I did, I would then take the 2 inside the root, which means it's instead of 2, it's the square root of 4. So 4 times 7 is 28. Notice that this is absolutely not what I would get if I took 175 minus 63. So that is not a correct strategy. If I want to square a binomial here, remember that I don't have a property that allows me to distribute that square across an addition. So that is absolutely not what I do. What I do is remember that squaring means to multiply something by itself. And now I have a binomial times a binomial, and now I can start distributing. So there are 4 multiplications that have to happen here. 5 times 5, 5 times 2 root 7, 2 root 7 times 5, and 2 root 7 times 2 root 7. So 5 times 5 gives me 25. 5 times 2 root 7 gives me 10 root 7. 2 root 7 times 5 also gives me 10 root 7. And 2 root 7 times 2 root 7, I'm going to write this as 2 times 2, which is 4, root of 7 times 7, which is 49. I'm going to write that out. But obviously, root 49 just is 7. So 4 times 7 is going to give me 28. So this term right here is really just 28. So I can add that 28 to the 25, and I have 53. And 10 root 7 plus 10 root 7 is 20 root 7. So this is what we get when we square 5 plus 2 root 7. We get 53 plus 20 root 7. One last concept, and that is that when we have irrational numbers, so something like, for example, 2 root 7, we can use a symbolic representation of the exact value. That's what this is. This is a symbolic representation of the exact value of that expression. But the square root of 7 is not a rational number, so I can't write it out as a decimal number and have it be exact because that is an infinite decimal number with no repetitions. So at some point, if I'm writing down decimal values, it's an approximation because I'm going to eventually have to stop writing digits, and then that's going to be not quite exact. If I want my answer expressed as an exact value, then I express it the way I've been expressing all of these before here. Root 5 is an exact value. 90 root 2 is an exact value. If I have, root 3 divided by 2, or 12 root 7 minus 3 root 5, these are all exact values. If I want just an approximate value, then I would need a decimal approximation. So if we consider 2 root 7, so this is the exact representation of the answer. If I wanted a decimal approximation, I could find a decimal approximation of root 7 and then multiply that by 2. But this is where it's almost always easier to use the whole radical. So if I consider that 2 root 7 is equivalent to root of 28, it's a little bit easier to estimate the value of root 28. So root 28 is going to be a little bit bigger than 5 because the square root of 5 is 25. But square root of 6 is 36, so we're ways away from that. So I'm going to approximate it and say, you know what, that's probably about 5.2. Now, it turns out, if I actually put this into my calculator, that it's closer to 5.29, so 5.3. But if I was just doing this using mental arithmetic, then 5.2 or 5.3 would be a reasonable approximation to make based on that radical. So this representation is just an approximate value because there are more decimal places after that 9.